All right, today we're going to dig deep into one of nature's most powerful and honestly terrifying forces, earthquakes. We all kind of know what it feels like when the ground shakes, but what's really going on, miles beneath our feet? To really get a sense of the scale we're talking about, let's just start with a single massive number.
36,000. Just let that sink in for a second. That's the number of people who were killed along the coasts of Java and Sumatra when the Krakatoa volcano erupted. It caused an earthquake that unleashed tsunami waves, get this, 40 meters high. That's just an absolutely staggering level of impact.
So that Krakatoa event, it's a perfect example of the devastating effect of an earthquake, right? But what is an earthquake, really? Like, at its most fundamental level, what is happening to the ground we stand on?
While the textbook definition is pretty straightforward, it's a sudden shaking of the ground caused by movements or tremors in the Earth's crust. But the key words there are sudden and crust. This isn't some slow, gentle shift. No, it's an abrupt, incredibly powerful release of energy from the planet's hard outer shell.
Okay, so this brings up a really crucial distinction. You've got the focus, that's the spot deep, deep underground where the rock actually breaks or slips. But then you have the epicenter. That's the point right on the surface, directly above the focus. And because it's the closest point on the surface to all that released energy, well, that's where the shaking is going to be the strongest and the damage is usually the worst.
Right, so a sudden movement in the crust causes all this shaking. But that begs the question, what in the world is powerful enough to move these enormous sections of the Earth's crust in the first place? What's the engine driving this whole thing?
And the answer, it turns out, lies in one single powerful idea, the plate tectonic theory. This quote here really says it all. It's become the accepted explanation. It's the theory that finally unlocked the whole mystery of earthquakes and explained why our planet is so active.
So what's the big insight here? It's that the ground beneath our feet isn't one solid piece, not at all. The Earth's crust is actually broken up into these massive plates. We're talking about 6 major ones and maybe 20 smaller ones. And they're all just floating on this semi-molten layer, constantly moving. They're being pushed around by these huge convection currents deep inside the mantle. It's kind of like a giant, super slow-motion boiling pot.
And this is basically how they interact. You've got 3 main ways. Plates can pull apart from each other, that's called diverging, and it creates rifts. They can crash right into each other, or converge, that's actually how the Himalayas were formed, or they can just slide past one another along what we call fault lines. And here's the kicker. Pretty much all tectonic activity, especially earthquakes, happens right along these plate boundaries.
Okay, so the plates move, the rock breaks down at the focus. And then what? How does all that energy travel from deep inside the Earth all the way to the surface to shake our cities? Well, it travels in waves. Seismic waves, to be specific.
The first ones to show up are the primary waves, or P waves. The P also stands for push. You can think of them like a sound wave, or maybe even better, like a shunting train where one car bumps into the next one in line. They literally compress and expand the rock as they move through it. And they're fast, the fastest of all the waves. And they can travel through solids, liquids, and gases.
Right on their heels are the secondary waves, or S waves. Now these are the shake waves. Instead of pushing and pulling, they move the ground up and down, or side to side, at a right angle to the direction they're traveling. And here's a really key detail about them. They can only travel through solids. They can't pass through liquids, which actually tells us a lot about the Earth's core. But that's another story.
And then the last ones to arrive are the surface waves. And yeah, as the name suggests, they're trapped near the surface. They travel more like waves on the ocean, with that rolling motion. Now, they're the slowest of the 3, but don't let that fool you for a second. That rolling, churning motion is exactly what causes the vast majority of damage to buildings and everything on the surface.
So you've got all these different waves and movements happening at once. How on earth do scientists even begin to quantify the power of an earthquake? How do you put a single number on something that can shake an entire continent?
Well, we use the Richter scale. It's designed to measure the magnitude, which is really just a fancy way of saying the amount of energy that gets released at the earthquake's focus. And the most important thing to know about it is that it's a logarithmic scale, which has some pretty dramatic implications.
What does logarithmic mean here? It means that for each whole number you go up on the scale, the shaking amplitude, the size of the waves, jumps up by 10 times.
So a magnitude 2 earthquake isn't just a little stronger than a magnitude 1. Nope, the shaking is 10 times greater. And that's just the beginning.
Because this is where it just gets mind-boggling. That same math means an earthquake with a magnitude of 8 has vibrations that are 1 million times greater than an earthquake with a magnitude of 2. It's not a ladder, it's a rocket ship. The difference in energy is just astronomical.
Okay, so now that we've got a handle on what they are, what causes them, and how we measure them, let's zoom out and look at the bigger picture. Where do these things usually happen? And what are their ultimate effects on our world?
First off, earthquakes are definitely not random. They're highly concentrated right along those plate boundaries we were talking about. A whopping 65% of all earthquakes happen around what's called the Circum-Pacific Belt. You've probably heard of it as the Ring of Fire. Then another 21% happen along the Mid-Continental Belt, which runs through places like the Himalayas.
Now, the destructive effects, that's what we're all most familiar with. And it's not just the shaking itself that collapses buildings. Earthquakes trigger this whole cascade of other disasters. You get fires from broken gas lines, landslides that can literally bury entire towns, and of course, those terrifying tsunamis, which is a Japanese word that means harbor wave, that happen when the seafloor itself is suddenly shoved up or down.
But here's something that might surprise you. Earthquakes aren't just destructive. They are also, believe it or not, a fundamental constructive force for the planet. By releasing all that immense stored-up energy, they're kind of like a planetary pressure release valve, helping the Earth maintain its overall shape. They build mountains, they create brand new landforms, and sometimes their landslides even block rivers to form new lakes. So in a very real sense, they're part of the planet's building process.
So that leaves us with this really fascinating question, doesn't it? When the same exact force can both shatter a city and build an entire mountain range, how should we view our restless planet? It's a powerful reminder that we live on a dynamic, breathing world that is constantly reshaping itself right under our feet.